must patiently wait for 22 hours before receiving any confirmation or response from Voyager 1. This time delay poses unique challenges for the mission team, demanding meticulous planning and precise execution of commands. Any errors or issues can result in additional delays and complications, particularly when investigating anomalies like the one experienced by Voyager 1. The time delay prolongs the diagnostic and troubleshooting processes, necessitating careful crafting of commands to account for the expected response time. Therefore, each time a message is received, it adds valuable information rather than being a mere waste of time. Furthermore, the time delay limits real-time control and interaction with Voyager 1. Unlike missions within our solar system where the time delay is relatively small, interstellar distances introduce a substantial lag in communication. This makes it impractical to conduct instantaneous conversations or make swift adjustments based on real-time observations. Regarding the anomaly's resolution, the mission team ultimately fixed the issue at the source by shutting down the faulty computer within Voyager 1. However, the most intriguing aspect of this situation remains the mysterious cause behind why the Altitude and Articulation Control Subsystem, AACS, began routing telemetry data to the incorrect computer. While it is suspected that the AACS received a faulty command from another onboard computer, the exact root cause of this anomaly has yet to be conclusively determined. Possible reasons behind the anomaly indeed. Within the boundless realm of space, there exist several plausible explanations for the anomalies encountered during Voyager 1's journey. The cosmic environment, while inspiring, can also prove to be a harsh and capricious adversary for spacecraft such as Voyager 1. Among the myriad of challenges, cosmic radiation, extreme temperature fluctuations, and the potential for micrometeoroid impacts are but a few of the environmental factors that pose a looming threat to the delicate electronic systems housed within the spacecraft. Cosmic radiation, composed of high-energy particles emanating from distant stars and various celestial sources, permeates the vast expanse between galaxies. Within this particle spectrum, one finds protons and cosmic rays, which possess the capability to penetrate spacecraft structures, potentially disrupting the proper functioning of electronic components. The sheer intensity of this radiation can trigger electrical disturbances, distort data signals, and even induce memory errors or data corruption. In such an environment, it becomes conceivable that Voyager's onboard computers may experience bewilderment, leading to the transmission of inaccurate data. In the unforgiving vacuum of space, spacecraft are also confronted by extreme temperatures, presenting a formidable challenge. Voyager 1, positioned in the outer reaches of our solar system, contends with frigid conditions, with temperatures plummeting to as low as -202 degrees Fahrenheit. These pronounced temperature fluctuations can significantly impact the performance of electronic components, potentially triggering unforeseen behaviors or errors in data transmission. However, the challenges do not conclude there. The presence of micrometeoroids, minuscule dust particles or fragments originating from comets and asteroids, further compounds the hazards facing spacecraft. Despite their small size, these micrometeoroids traverse space at remarkable velocities, rendering them capable of causing damage upon impact. Even a minute collision with a delicate electronic component can disrupt its functionality or introduce interference in data transmission. While these are conceivable explanations for the anomaly, there is another hypothesis that has garnered attention within the scientific community, a notion that transcends mere technical glitches. This intriguing idea suggests that the anomaly may not be attributed to a malfunctioning computer, but rather to an intentional manual intervention. We are delving into the realm of the possibility of extraterrestrial involvement, aliens. The proposition is that there might exist an exceptionally advanced extraterrestrial civilization possessing capabilities far beyond our own. These extraterrestrial beings could wield cutting-edge technology and possess an extensive comprehension of space exploration. Given that Voyager has ventured to exceedingly remote distances from Earth, it becomes plausible that it has traversed into alien territory occupied by beings too distant for us to detect. Since Voyager is engineered to relentlessly seek out additional data, it could have conceivably stumbled upon this civilization and embarked on an endeavor to gather more information. Yet, instead of encountering a malfunction, it may have been taken over, leading to the anomalous behavior. In this context, what we initially perceived as a malfunction might actually be an extraordinary discovery. However, if such an event did transpire, how would we ascertain its occurrence? The question lingers as we grapple with the vast expanse of space and the limitations of our current technology and understanding. Understanding how Voyager works, the key to unraveling this enigma potentially lies within the intricate communication system employed by Voyager 1. This spacecraft relies upon NASA's Deep Space Network, DSN, to establish vital connections with Earth. Within this network, there are 3 ground stations on Earth, each equipped with a formidable 37-meter diameter high-gain Cassegrain antenna. This specialized antenna plays a pivotal role in enabling Voyager 1 to transmit and receive radio waves, particularly the one that perpetually remains directed towards Earth. One of the key factors contributing to the spacecraft's enduring functionality lies in its dual redundant computer systems. Each Voyager spacecraft boasts 2 sets of command computer subsystems, the Flight Data Subsystems, FDS, and the Altitude and Articulation Control Subsystems. This redundancy ensures seamless transitions between systems and the ability to activate dormant computer components, effectively extending their lifespan. Efficiency was paramount during Voyager's mission design. To work within the constraints of power budgets and time limitations, electrical engineers developed simplified systems using hardwired logic for the spacecraft's instruments. Consequently, Voyager 1, along with its twin Voyager 2, features 6 onboard computers organized as a distributed system with 3 dual redundant pairs. This innovative approach has allowed the spacecraft to defy the rapid ages of time and continue delivering invaluable data from the depths of space. Power management, maintaining the operational functionality of Voyager 1's computer systems remains a pivotal endeavor due to the spacecraft's constrained onboard power resources. Engineers have devised a range of strategies to conserve and optimize power utilization, a crucial aspect of its sustained mission. The Voyager probes are both equipped with radioisotope thermoelectric generators, RTGs, as their power source. These nuclear power supplies gradually lose about 4 watts of energy per year due to the slow decay of the plutonium they rely on. This natural decay process produces heat, which is then efficiently converted into electricity to sustain the probe's operations. One noteworthy aspect of power management involves the selective deactivation of non-essential systems. Engineers follow a systematic process to identify and power down components or subsystems that are not integral to the primary mission objectives. For instance, heaters associated with specific scientific instruments have been intentionally deactivated. While these heaters were originally designed to uphold instruments at precise temperatures for optimal performance, deactivating them significantly curtails power consumption, thereby extending the overall lifespan of the spacecraft. However, it's crucial to address the challenge of extreme cold temperatures that Voyager encounters in space. Scientists must ensure that the propellant lines remain sufficiently warm, typically around 2 degrees Celsius. Maintaining this temperature is essential because if these lines were to freeze, scientists could risk losing their ability to accurately point the spacecraft toward Earth. Therefore, managing the spacecraft involves a delicate balance between power generation, thermal control, and operational considerations to ensure its continued functionality. Voyager 2 has initiated the utilization of a modest backup power reserve that was originally integrated as part of a safety mechanism. This backup power source will enable the spacecraft to maintain the operation of another scientific instrument until the year 2026. The safety mechanism, designed to safeguard the spacecraft's instruments in the event of substantial electrical fluctuations on board, included a limited power reserve serving as a backup circuit. This contingency power source is proving invaluable in extending the functionality of the spacecraft's scientific instruments. That said, as the power supply on the Voyager probes gradually diminishes, conserving energy becomes paramount, impacting various systems beyond the scientific instruments. One crucial system affected by this dwindling energy budget is the spacecraft's heating mechanism. Generating heat is an energy-intensive process, and as the available power decreases, more heaters may need to be deactivated to ensure the continued operation of the remaining instruments. These probes are equipped with small thrusters, which play a critical role in their functioning. Proper orientation of the spacecraft, ensuring their antennas face Earth, is essential for receiving commands and transmitting data back to our planet. Each spacecraft carries a tank of hydrazine monopropellant fuel that powers these small thrusters, which operate by emitting brief bursts or puffs to adjust the spacecraft's orientation. In the event that the fuel lines leading to the thrusters were to freeze, engineers would lose the ability to control the spacecraft's orientation and, consequently, its instruments and antennas. At that point, the probes would likely become inoperative, underscoring the importance of maintaining an adequate heat supply for the thrusters. However, there is an additional challenge with the thrusters themselves. Over time, like any mechanical system, they may experience wear and breakdowns. In 2017, engineers noticed that some of Voyager 1's thrusters were working harder to maintain the correct orientation toward Earth. To address this issue, they decided to activate a set of secondary thrusters that had been in use for an astonishing 37 years. Remarkably, these long-dormant thrusters performed admirably, highlighting their robustness and reliability. Now, the primary thrusters on Voyager 2 are exhibiting signs of wear and tear. Building on the success of reactivating Voyager 1's dormant thrusters, engineers are planning to engage the backup thrusters on Voyager 2. These backup thrusters, though not as dormant as Voyager 1's, have still been in use since Voyager 1's encounter with Neptune in 1989, marking approximately 30 years of inactivity. NASA intends to initiate this activation. Engineers and mission planners believe that there are still several years of operational capability left in these remarkable spacecraft. This extended operational life is of utmost significance because the unique vantage point of the Voyager probes allows them to provide invaluable insights into the region of space they are currently exploring. Hopefully, the day the Voyager powers down is a long time away. On that note, the decision to power down non-essential systems is not made impulsively. It entails a meticulous evaluation of the trade-offs between power conservation and the mission's scientific objectives. Engineers collaborate closely with scientists to assess the impact of deactivating specific systems on the quality and availability of scientific data. The objective is to strike a balance that maximizes power efficiency while preserving the necessary functionality to continue amassing valuable cosmic information. In addition to selective power reduction, engineers implement adaptive power management strategies that respond to the spacecraft's evolving environmental conditions. As Voyager 1 journeys farther from the Sun, the available solar energy diminishes. To compensate for this, the spacecraft adjusts its power usage accordingly. This adaptive approach ensures that available power resources are allocated efficiently to support crucial operations and data transmission. Furthermore, ongoing technical advancements and enhancements in power management techniques have enabled engineers to refine and optimize the power systems of the Voyager probes over the years. These improvements encompass more efficient power distribution, enhanced battery charging methods, and advancements in power regulation and control. Through these methodical power management strategies, engineers have successfully extended the operational lifespan of Voyager 1, enabling it to continue its remarkable scientific exploration through the depths of space. The careful allocation and conservation of power resources ensure that critical systems remain operational, allowing the spacecraft to transmit valuable data and insights back to Earth. Even though it was initially designed for a mere 5-year mission, this accomplishment is a testament to the dedicated efforts and expertise of the scientists and engineers who have worked diligently to keep the Voyager mission alive in deep space. However, it's important to acknowledge that unexpected events can still occur in the vastness of outer space. Deep space is known for its unpredictability, but even so, we do possess some level of understanding regarding the potential scenarios and challenges we may encounter. Anomaly, one would naturally anticipate that a spacecraft like Voyager, during its journey through the cosmos, would primarily encounter celestial objects such as meteoroids, asteroids, and other spaceborne entities. However, the receipt of messages from Voyager 1 indicating the detection of a staggering 500 objects marked a profoundly unusual turn of events. This unforeseen development was promptly classified as an anomaly due to the signal's abrupt and unanticipated arrival, presenting the research team with a perplexing enigma. While the anomaly introduced a slight communication delay, Voyager 1 continued to exhibit its characteristic responsiveness to commands from a dedicated team at Mission Control. Notably, the spacecraft's reliable antenna remained directed towards Earth, thereby ensuring the effective reception and execution of instructions. While scientists grappled with the confounding data, Voyager 1 itself appeared to dutifully adhere to its expected operational behavior, diligently gathering and transmitting valuable scientific information. It's worth highlighting that this anomaly failed to activate any of the onboard fault protection systems explicitly designed to spring into action upon detecting irregularities. These systems, typically responsible for placing the spacecraft in a safe mode, thereby enabling engineers to conduct comprehensive investigations and diagnose issues, remarkably remained dormant. Voyager 1 intriguingly continued its mission activities without any trigger for a protective shutdown, thereby adding yet another layer of complexity to this mysterious episode. Investigating the anomaly following a meticulous and thorough investigation, the root of the anomaly was conclusively traced back to the Altitude and Articulation Control Subsystem, AACS, which bears the critical responsibility of precisely orienting the spacecraft and managing its intricate movements. The puzzling revelation was that the AACS had been unintentionally transmitting telemetry data through an onboard computer that had ceased to function many years ago. This outdated dormant computer, which should have had no role in data processing, inexplicably became intertwined with the telemetry transmission process, leading to the unfortunate corruption of information being relayed back to Earth. The paramount question that loomed large was whether there truly existed a swarm of 500 objects that had triggered Voyager 1's perception of a potential threat. Confirmation of this intriguing discovery remained elusive until the time-consuming anomaly could be satisfactorily resolved. The ingenious solution to this enigma ultimately involved the issuance of instructions to the AACS, directing it to redirect telemetry data to the appropriate fully operational computer system. This corrective measure was deemed to carry minimal risk and was subsequently executed with precision and success. Nonetheless, the investigation into this anomaly posed a substantial and unique challenge, primarily due to the vast time delay in communication, an inevitable consequence of Voyager 1's staggering distance from Earth. After its extraordinary interstellar journey, the spacecraft now resides at an astonishing distance of approximately 14.6 billion miles from our home planet. Consequently, radio signals transmitted to and from the spacecraft traverse an expanse of space so immense that they require a considerable amount of time to complete their journey. This temporal chasm in communication presented a profound challenge for the mission team. Their tasks demanded meticulous planning, cautious execution of commands, and the patient endurance of lengthy periods before receiving any feedback or confirmation from Voyager 1. This peculiarity in the communication process significantly extended the timeline for diagnostic and troubleshooting efforts. Each message transmitted to the spacecraft, although subject to the arduous constraints of time, held the potential to unravel the mysteries of space and deepen our understanding of the cosmos. Communicating with the Voyager, when NASA's Deep Space Network, DSN, team sends a command to Voyager 1, it travels as a radio signal at the blazing speed of light. The Deep Space Network is a sprawling network of colossal radio antennas strategically positioned across the globe. Its purpose is to establish vital communication links with spacecraft exploring the far reaches of our solar system and beyond. It plays a crucial role in enabling two-way communication between Earth and deep space missions and conducts radar and radio astronomy observations to enhance our understanding of the universe. This international network collaborates with various space agencies, including the Soviet, Chinese, Indian, and Japanese deep space networks, as well as the European Space Agency's ESA tracking system. By working together, these agencies create a unified and cooperative effort to explore and investigate the mysteries of space. The DSN consists of 3 deep space communication facilities situated approximately 120 degrees apart. These locations include Goldstone in California's Mojave Desert, Madrid in Spain, and Canberra in Australia. This strategic positioning ensures continuous coverage and observation of spacecraft as the Earth rotates, making the DSN the largest and most advanced scientific telecommunication system worldwide. Operating on the principles of radio wave transmission, the DSN communicates with spacecraft using its colossal antennas. These antennas are responsible for sending and receiving radio waves, establishing a vital link between Earth and the distant probes. When transmitting data from the spacecraft to Earth, Deep Space Network Channel 18 is typically utilized, employing frequencies of either 2.3 GHz or 8.4 GHz. Conversely, when sending signals from Earth to Voyager 1, a frequency of 2.1 GHz is employed. And all of this communication happens at the speed of light. However, even at this remarkable speed, the signal requires approximately 22 hours to reach the spacecraft. This means that after transmitting a command, the mission team. In its typical operations, Voyager 1 utilizes Deep Space Network Channel 18 for transmitting essential data back to Earth. To transmit data, the frequencies it operates on are typically of either 2.3 GHz or 8.4 GHz. The signals from Earth to Voyager are transmitted at 2.1 GHz. However, in scenarios where direct communication with Earth becomes momentarily unattainable, Voyager 1 is equipped with a digital tape recorder. This recorder has the capacity to store approximately 67 megabytes of data, which can be sent until a later time when communication can be re-established. Consequently, scientists possess the means to conduct comprehensive analyses of the data recorded during the period of malfunction. This valuable information could hold the key to determining whether the involvement of extraterrestrial entities such as aliens is a plausible explanation for the anomaly. But that's not all. If Voyager 1 did indeed establish contact with extraterrestrial beings, it possesses a suite of instruments meticulously designed to gather exceptionally detailed information. The spacecraft boasts an impressive array of scientific instruments, each with its own distinct purpose. These instruments are integral components of the attitude and articulation control subsystem, responsible for maintaining the spacecraft's stability and ensuring its radio antenna remains accurately oriented toward Earth. Among the scientific instruments nestled within Voyager 1's payload is the cosmic ray subsystem, which diligently measures the intensity and properties of cosmic rays. This invaluable data sheds profound insights into the cosmic environment that extends far beyond our Sun's influence. Working with the cosmic ray subsystem is the magnetometer, a precision instrument dedicated to the meticulous analysis of the strength and orientation of magnetic fields encountered in the vast expanse of space. In doing so, it contributes significantly to our comprehension of the intricate interplay between the solar wind and the expansive realm of interstellar space. The photopolarimeter subsystem plays an equally vital role by capturing and dissecting light, particularly polarized light. Through its observations, scientists gain deep insights into the composition and unique characteristics of interstellar dust particles and other celestial entities, enriching our understanding of the cosmos. Complementing these instruments is the plasma science instrument, which delves into the properties of charged particles known as plasma. This specialized instrument provides invaluable data pertaining to the density, temperature, and velocity of these charged particles, offering profound insights into the dynamic nature of plasma within the interstellar medium. In essence, Voyager 1's extensive array of scientific instruments is poised to unlock the mysteries of any potential encounter with extraterrestrial civilizations should such an extraordinary event have occurred. Moreover, in Voyager 1's arsenal of scientific instruments, we find the low-energy charged particle instrument, tasked with the meticulous study of the composition and energy distribution of low-energy charged particles, encompassing electrons and ions. This in-depth examination yields invaluable insights into the origins of these particles and the intricate mechanisms propelling their acceleration across the vast expanses of space. Extending our exploration further, we encounter the plasma wave subsystem, an instrument designed to detect and analyze naturally occurring radio and plasma waves. Through its capabilities, scientists gain the means to investigate the properties of the interstellar medium and delve into the intricate dance between the solar wind and its cosmic surroundings. Venturing into the spectrum of light, Voyager 1 carries the ultraviolet spectrometer, a device dedicated to the meticulous measurement of the intensity of ultraviolet light emanating from various celestial objects. This enables the spacecraft to conduct a comprehensive examination of the composition and physical properties of gases within the interstellar medium. The infrared radiometer, a valued companion in this cosmic journey, contributes by analyzing the thermal emissions of encountered objects. This analysis unveils essential insights into the temperatures and thermal characteristics of these cosmic entities. In tandem with the infrared radiometer is the interferometer, which scrutinizes the interference patterns of infrared light, further enriching the scientific treasure trove of data gathered during this extraordinary voyage of exploration. This intricate suite of scientific instruments equips Voyager 1 with the capabilities needed to scrutinize the composition and physical properties of gases and particles it encounters during its cosmic odyssey. By unraveling the intricate details of the interstellar medium, scientists gain invaluable insights into the cosmos. While these dedicated scientific instruments diligently collect data, the high-gain antenna serves as the communication lifeline, ensuring that their findings are efficiently transmitted back to Earth with a robust and unwavering signal. This antenna plays a pivotal role in facilitating continuous and effective communication between Voyager 1 and Mission Control, enabling us to receive the invaluable treasure trove of knowledge amassed by these instruments. Indeed, the wealth of data accumulated has proven to be a veritable treasure trove. Voyager 1, alongside its companion Voyager 2, delivered a historic breakthrough in 1993 when they provided the first direct evidence of the heliopause. A momentous discovery, the heliopause signifies the boundary that demarcates the transition between the solar wind emanating from our Sun and the all-encompassing interstellar medium. This revelation offered incontrovertible confirmation of a distinct boundary delineating our solar system from the boundless expanse of interstellar space. This epochal discovery proved to be pivotal in enhancing our comprehension of the outermost boundaries of our solar system, shedding light on the intricate interplay between our radiant Sun and the enigmatic interstellar milieu that surrounds it. During its captivating encounters with Jupiter and Saturn, Voyager 1 unveiled a treasure trove of knowledge concerning the moons and majestic rings enveloping these colossal gas giants. At Jupiter, Voyager 1 identified a hitherto unknown ethereal ring delicately encircling the planet. Moreover, it unveiled the existence of two newfound moons, Thebe and Métis, enriching our understanding of Jupiter's lunar population. In a parallel vein, as Voyager 1 ventured forth to Saturn, it unraveled a tapestry of 5 previously undiscovered moons and introduced us to a novel ring aptly christened the G-ring. These revelations expanded the frontiers of our knowledge regarding the intricate systems of moons and rings that orbit these majestic gas giants, offering profound insights into their genesis and dynamic evolution. Yet, among Voyager 1's most captivating discoveries was the presence of active volcanoes adorning the moon Io, a celestial companion of Jupiter. Voyager 1 bore witness to the awe-inspiring spectacle of plumes of erupting lava surging skyward to astonishing heights, often reaching hundreds of miles above the moon's surface. These eruptions showcase the profound geological activity unfolding within our celestial neighborhood, painting a vivid portrait of the dynamic forces at play in the cosmos. These mesmerizing volcanic eruptions on Io are set into motion by the captivating ballet of tidal interactions that unfold between Io, Jupiter, and its other lunar companions. This remarkable revelation not only expanded our understanding of the sheer variety of dynamic processes transpiring beyond Earth, but also showcased the unique and mesmerizing characteristics exhibited by celestial bodies within our solar system. Voyager 2, Voyager 1's counterpart, embarked on its own extraordinary journey of exploration. Together, these intrepid spacecraft have ventured beyond the confines of our solar system, delivering a wealth of knowledge and expanding the horizons of human understanding. As they continue their cosmic odyssey, Voyager 1 and Voyager 2 serve as beacons of exploration, inspiring future generations to reach for the stars and unravel the mysteries of the cosmos.